And finally, we have our main speaker today will be Adam Jacoff. Adam is with the Engineering Laboratory in Gaithersburg, Maryland. Adam is a robotics research engineer, and he's worked on robot development, but then that was a more early career. And then now he is working more on test development. So developing tests to evaluate robot capabilities, but also the user's capabilities. Adam has worked on that extensively, and he's won numerous awards for service, for excellence, and innovation. And the tests that he and his team and Therese and her team that they have been working on are used worldwide by organizations all across the world to increase our collective public safety capabilities. So without further ado, please give a warm welcome to Adam Jacoff.
Well, thank you very much. As Kara said, I'm in the Intelligent Systems Division of the Engineering Laboratory. So the Intelligent Systems Division is really focused on all the machines that are out there in the world that are doing some thinking for themselves. You hear the term artificial intelligence thrown around a lot lately. Well, our division's been around for a while, and we know in our bones that that is the secret sauce to making all of these robots, drones, and aquatic vehicles work, especially in the hands of rather unskilled operators who have other priorities for their jobs. So I'm going to take you through the process of developing standard test methods to evaluate these systems, and as Kara mentioned, the operators behind them. So just an example of why we do what we do. So emergency responders in general are in harm's way like every day. Their day jobs look a lot different than our day jobs. The idea of a person walking to an unknown vehicle in a padded suit past a perfectly functional robot is one of those situations that drives us. We could have told them, and they probably already knew that that robot was not going to be able to open those doors or look inside. There's test methods that help us evaluate that, help us measure their ability to do that. They use those test methods to train their operators. What probably happened here is maybe it would have been successful eventually, but it wasn't going to be fast enough to keep up with the pace that emergency responders need to maintain. So this is just one example, but think about like a collapsed structure. Earthquake brings down most of the building. The rest of the building needs to be searched, but it's unstable. You don't know if it's going to all come down. So sending responders in, as brave as they are, as capable as they are, as competent in their skills as they are, is still not the right move when there are machines that can go in and present that remote standoff. So here's an example of the state of the commercial market right now. This is a fairly recent commercially available robot that's gaining popularity. The whole idea of the legged systems with a multi-degree of freedom arm that's coordinated is what the Intelligence Systems Division all along was striving toward. Now our tests, we got out of the business to the degree of making the robots themselves, and we started guiding the community with these standard test methods. Here it is right out of the box. Couple of pushes. Yeah, the hinges are on the left. Yeah, it's a pull door, no step. Go. And the rest of it, it's thinking for itself. So keep an eye on its front paw. You don't think about how you actually go through doorways, but these machines need to think about every single move. And that is a pretty special move right there. That is what autonomy brings to this game. So it's not always about opening doors. It's not always about looking in things. Sometimes it's just a matter of getting downrange in a chaotic and difficult world. Rubble piles would be the extreme example, but just everyday humanity inside our houses. Think about how messy your house is. Think of that, you have stuff on your stairs. That is the least of it, and the robots need to be able to handle getting downrange. There's also other tasks for them to do. Sometimes they need to deploy tools. Sometimes they need to carry things. Sometimes they need to go get something from in the world and bring it back. Sometimes they need to start with the responders and they need to go downrange. Like when they find a victim in a collapsed structure that isn't healthy enough to bring out immediately, they need to bring water in. They need to bring communications in. So getting there is part of the problem. So we've designed a series of test methods to help both inspire the innovation that's required and to measure the systems that are ready for commercialization and help those manufacturers convey that they're ready for deployment when it's time for responders to start purchasing robots. So these are all examples of standard test methods. So what is a standard test method? It's just an apparatus, well described, easy to replicate. In our case, we make them very easy to replicate. We have a very small palette of features that you would find in any big box store so that they can be replicated in Germany and Japan, certainly all over this country. So it's an apparatus. It's a procedure, nothing more than a list of things to do in order so that you can make sure everyone's doing the same thing in that test apparatus, and then some sort of score, some sort of metric. Maybe it's just back and forth, back and forth, back and forth 10 times, always 10 times, maybe 20 times, never just once, never twice. That's luck, good or bad. So a standard test method produces quantitative scores with statistically significant capabilities being measured. Now, you may have heard of equipment standards. They're really useful. You may have heard of performance standards. That means that I can jump as high as I'm supposed to jump for this job I'm seeking. Those are all important too. That's not what we're doing. We're developing the underlying standard test method that everyone else uses for their own purposes. So here's actually one of the first ones. This was called the step fields. This is the easier variant of the step fields. They started as random step fields, much more chaotic, much more rubble pile-ish, but they were not repeatable, forwards and backwards for multiple repetitions, and that's a cardinal rule in standard test methods. Every repetition needs to look the same. So here you see there's one at NIST with this kit wheeled robot. There's the legged one you just saw, but that happens to be in England. In the competitions in Australia, that's a Japanese robot in an Australian step field. That is what standard test methods get you. They get you direct comparisons no matter where or when that trial happened. And it's not just for mobility and dexterity. We have a lot of tests for sensors and things. This is in the competition space, which I'll talk about a little bit more later. But back to the original scenario where we had the vehicle. Ideally, they would go down and want to break glass. It seems like a natural thing to be able to do remotely, but it's not. It is not easy. It has a lot to do with the tool. It has mostly to do with the situational awareness from the remote operator. So the remote operator is sitting there looking at a monitor, which means they have no depth perception, like at all. It's you watching your TV. Even if they have goggles on, they're not as capable as you are in present with that task. So it's very difficult. This is how we know it wasn't going to be able to break windows. We can put them through this test and let the clock go and count how many times they break it in how much elapsed time. But maybe what they need to do is look at the next generation of capabilities. Could be a drone with this spinning tip on the end, and that spinning tip makes contact and the window breaks. Whatever that advanced technology is, it's the same test method measuring whether it's working or not. Exact same test method, two completely different approaches. First chance to get to compare them side by side for their relative merit, their relative expense, their relative ease of use. Whatever that is, that's not our decision. That is the emergency responders who buy those products. So here's some more examples. Left side, you have ramps. This is in the competitions. These are fully autonomous robots now. Competitions are focused on full autonomy as much as we possibly can. The one on the left is actually scanning with a laser, trying to figure out the world that it's in, and it's in a pretty difficult situation. The one with legs went downrange the first time manually, mapped the whole thing, and then it used that map back and forth to finish the 10 repetitions. We don't care. Scores are scores. The idea is that the apparatus, the procedures, and the performance metrics are helping people to discriminate between the two systems. Another Example of the competitions are, we don't just do stairs, we do occluded stairs with debris on it. That left-hand robot there with the body tracks and 4 independent flippers, well, that's a whole lot of things to control for a remote operator. It takes coordination, which means it takes some intelligence on board. That Japanese robot invented that style of robot because of the step fields I showed previously. This test method came from the fact that that robot was deployed into the Fukushima Daiichi nuclear disaster in Japan. Big nuclear disaster where there was dust everywhere and radiation, and we couldn't send responders in because it was very, very dangerous. This is the only robot that could go in and climb 5 stories to map the radiation throughout the building. Of course, they sent at least a dozen other robots to try to do the same task. Military deployed, everyone wanted to help. But they ended up coming after the academic team from this competition because it was best-in-class mobility in the RoboCup Rescue Robot League. So it had been born and raised on these test methods. Meanwhile, the one on the right, current champion, is from Thailand. There are 100 teams in Thailand that took the design from Japan, which they freely shared, and refined it further. So Thailand, with 100 teams, perfected this idea of body tracks, 4 independent flippers, remote situational awareness. So the test method is somewhere in between the two. So that was the most aggressive form of the test method in the competitions because we're pushing on the researchers to be more innovative. We're sometimes having to scale back for the commercial market to make sure that they can have measurable success. So clear stairs are kind of passé. Wet, metal, slippery stairs all need to be done, obviously. But the occlusions on the stairs are what we're doing now to upgrade the standards. A standard test method is not a static thing. It changes every 5 years. It has to stay out in front of the commercial market for sure, but probably right out in front of the state of the science. Just a little bit harder than the state of the science can handle. So every 5 years, we update it and reballot it for everyone to see. So multiple repetitions, looks like one fell. Falling is okay. Doesn't even show up except in a note. The idea is if you can get up and keep going, like you or I would, you're fine. Your time elapsed might be a little longer than usual. Whatever the task is, there are variables involved. In this case, this is just last month in Texas, I'm with 300 emergency responders. Half of them are firefighters, half are probably police, a little military, and they all have packages that they want on these robots to do their job for them. In this case, it's a fire hose. Fire hose in a burning building needs to get to the upper floors. Firefighters take everything with them in the upper floors. If it's a high rise, they're climbing 30, 40, 50 stories. They're not using the elevators. Having a robot be that Sherpa to help bring equipment up, help improve communications, maybe keep track of the responders that they're teamed with, there's a lot of value in getting these robots into that kind of mix. So this is the first test ever. We're belayed, so we're safe. Robots never get hurt in standard tests. That's a goal. And certainly no people. All right, so here you go. This is what happens when you fall. There's a test method for that. If the one on the left is in the easier terrain, the one on the right is in the harder terrain, if they fall, they just need to get back up. This is where the autonomy shines, right? The autonomy, this almost has to be an autonomous behavior because there's not a lot of information for the remote operator to even work with. His cameras might be in the dirt. Yeah, it's the most impressive thing you see these robots do is when they get up, dust themselves off and look back at you and say, is that all you got? So he looks happy. All the audience is happy. That's happening at a competition. There's probably 1,000 people watching. And just understand that it's not just dexterity and mobility, it's mapping of unknown environments. So the thing about robots being the first into these unknown semi-collapsed structures is they need to bring out information. They need to radio out information. They need to inform the wave of humans that are going to be the ones in there to do any rescuing. So these robots aren't rescuing anybody. They are mapping the environment. They are identifying hazards. They are identifying easy routes to get in. But then the humans are the ones that go in. So coming out with 2D or 3D maps is a very high priority for these systems. And so 1/3 of all the scores of our robot competitions is mobility, mapping, and dexterity. And just, because I have to show you a bar chart, there's a way to convey the performance of an entire system in very simple terms. In this case, let's just say these are the mobility tests chosen by our National Capital Region bomb squads. This happened to be in 2010. You can see all the terrains, kind of how simple they look at that time. That was literally all the commercial market could handle. That one on the right, the step fields, the original step fields, only 3 of these robots have a red bar because only 3 robots could do 10 laps in that terrain. No knock on them. Maybe they're not designed to do it. All we're saying is it was incomplete. If that's your terrain as a firefighter, then you want to pay attention to the red bars and maybe make your decision based on that. But you see, some bars are really tall, some are short, some are rather similarly short. One of those robots might cost like half of the other robot. So you can get 2 robots instead of 1 robot and have relatively similar performance. So this is how standard test methods kind of work in the commercial world to support competition and to help different manufacturers package their various capabilities. So the project objective, simply put, is to develop the measurement science, develop the standard test methods, capture the data that these responders need to help guide their decisions. We have a lot of tests now that are working in the ground robot spectrum, in the aerial drones, and in the aquatic vehicles, but they all essentially follow the same practices. Generally to promote innovation, we're the Commerce Department. That is one of our main goals. To make sure that competitiveness, for the U.S. against the whole world of robotics manufacturers is second to none. And then to improve the effectiveness and safety of those emergency responders at the end. I really should lead with that because that is really the most important part of this whole process. It's so they can be effective, A, and B, remote while they're being more effective. Because when we started, none of this existed, literally. So I'm talking like 2000, 2001 is when this standards stuff started. There was just no way to measure the robots' capabilities. The robots were clearly not doing what their responders needed. They were wasting money, they were wasting time, they were frustrated, it wasn't good. Putting some standard test methods in the middle of that mix tightened up the whole process. It allowed them to communicate up to the manufacturers what they want, not wait for things to just happen. No one in the manufacturers really knew what the responders do for a living, specifically. So they weren't designing to the right things. That's where the robot competition started changing the focus of the research and then the focus of the commercial world. All right, so you end up with 50 test methods. 50 test methods is a lot, but it's actually not even all the test methods we have. It's 50 in the standards process. So they're somewhere between being balloted and standardized, 23 of them are standard, or being validated actively, or they're done and they just need to be balloted, somewhere in that spectrum. So how do you know you're getting old? Well, one thing is you get one of these, plaques and pins from NIST. I've been here 35 years plus, so they tell me. 50 test methods is one indication. Having the NIST designated historian drop by your office to pick your brain about the early days, well, that's a real clue. So I figured I would take you, since, the idea here is to show you one engineer's meandering path through life, so maybe there is a lesson or two in here. I had no idea as an engineer what I wanted to do when I grew up. in high school, actually, I would say robotics wasn't really a thing. It was a notion, it was an idea. There were research programs dedicated to it, but they certainly weren't commercially available. This is like the 1980s. Junior in college, senior in college, I started understanding maybe a little more about why I stayed in the harder maths all along. And I recommend that to you. Take the hardest math classes you can for as long as you can. It will pay dividends. It will not only teach you how to think and how to be critical and how to solve problems, people will recognize it as that. And there'll be a lot of opportunities for you no matter what you do. I was thinking, coming out of this event, by the way, one thing about this event is that deadlines are just good for the soul. You need deadlines in your life. You need deadlines or the thing never quite gets done. In this case, a robot competition, it's either working or it's not. And guess what? This was a semester project that was not working. We go out to Colorado. I think it was the Air Force Academy where this was hosted. It's still not working. We're in a hotel room. We're up 2 days. It's still not working. We bring it to the venue. Start line is right there on a basketball court. It's still not working. It literally took its first steps across the starting line when they said go. First steps we ever saw it take. Feverishly working on it from start to finish, and more so in the end days. When it started working, it walked like a champ. It did exactly what it was supposed to do. It was designed to be really stable. It was slow, but it was walking. There's no question. And this, note that it's the walking machine decathlon. It's a machine, not a robot. Back in the day, this thing had no intelligence. Didn't even have a computer on board. There were no computers you could put on board. It was a machine. I did the legs. I teamed up with others in University of Maryland Engineering School, electrical engineers, and others who did their pieces of the puzzle. So you learn how to work as a team. You will do nothing in life alone. You will always be on a team. So take the sports metaphor seriously. You learn how to be a good teammate. Learn how to be a good leader. So I graduate knowing that I want to do something in robotics. Didn't really know what. Liked the idea of keeping people out of harm's way. Didn't really know what that meant. I get here, hired into the Intelligent Systems Division. It was called the Robot Systems Division at the time. First project, teamed me up with a guy who was just a couple years older than me, Al Wavering. He was actually a division chief. He just retired. And we built this Triclops, a robotic head, foveal peripheral vision. The idea was that it was supporting the research for building the space station. So it needed to track slow-moving things through space. So there was this shiny ingot that we slaved over and coddled into existence for probably 6 months, and then a $100,000 computer that made it do what it was supposed to do, and it moved, and it was beautiful. As a matter of fact, physically it's beautiful. It's in the lobby of the NIST admin building right here in one of those display cases. That was the idea of mechanical engineering. That's what my degree was in. What I realized I was missing was this notion of computer science. So I learned that I can build things as a mechanical engineer. I could build them big, I could build them strong, I can build them really, specifically to do a task maybe. But until they got the computer science on board, they were never going to be smart and they were never going to be useful. I learned that even more in the Automated Manufacturing Research Facility here. NIST is rather famous for instantiating that notion of lights-out facilities where robots reign. By the way, if you ever get a chance to go to a robotic assembly, like a car assembly plant, it's like the eighth wonder of the world, and it's not just because I'm a geek and I like that kind of stuff. It's amazing what they're doing. They're huge robots picking up very small things, very coordinated dances. Well, the idea of that coordination in such close proximity is where offline programming comes into play. That was my small role in that big AMRF. Develop a simulation so that you could practice your code virtually and see where the collisions happened before putting it on the expensive hardware. RoboCrane was actually kind of a pet project for the division. My mentor, the guy who instantiated the Intelligent Systems Division, Jim Albus, had this idea originally. It's a cable-based crane. It's a good remote control crane if you think about it. It doesn't spin, it doesn't swing, and so it has a whole lot of uses. In this case, we were focused on places people really ought not be, but we developed it in NIST, and then it gets licensed out into the commercial world and does things like stripping paint off planes. So we turned the terrible job, really the worst job at the Air Logistics Center, into kind of the coolest job, where they're sitting in an air-conditioned cab, they got country music playing, and they're swiping at this plane with these blast patterns that were just huge, where before that it was like, the energy pattern was like a nickel on a building, and you had to strip the paint off that building every day. So whatever it was, we had to invent some things here, and that's where the innovation comes in. It was a seed of an idea, and then the question is, how many different ways can you apply that idea? Should it be a good idea? Currently, still in the nuclear disaster in Chernobyl, near Kiev. Again, licensed to a commercial vendor who's implementing it, but the idea is the exact same. You know, you guys have actually seen this technology at work. The camera that's behind the quarterback in an NFL game, that camera is flying around the stadium on multiple cables. It happens to be 4 cables instead of 6 cables. And it's rather unstable, but it has a stabilized camera on it. It gives you those beautiful pictures from behind. That's the same idea. That's a remotely operated crane-like device. Army's Experimental Unmanned Vehicle, XUV, that was also invented here for the most part. At least the brain was invented here. Jim Albus designed that control architecture, a hierarchical architecture. Several of my colleagues back then implemented it in this first Army unmanned vehicle. Now you see robots driving around the streets that are unmanned. Well, this was the beginning of that in 2002 and 3. So I wasn't involved in the development, so I ran the trials. Me and my office mate and a couple of others who all had skills that we put together as a team to start evaluating somebody else's robot. Never did that before. This is where I learned that when you're directing such a big endeavor like that, or when you're running a concurrent competition with 20 teams, all with 10 people, with families and sponsors, that if your stuff doesn't work, the whole thing implodes, and you affect a whole lot more people. So deadlines. So that's what got me into the competitions, really. It was around 2000, did the first competition for the Association for the Advancement of Artificial Intelligence. It was pre-9/11, one summer before. Then 9/11 happened. We had an urban search and rescue focused competition for robots, and it just rolled on from there. All the robots from the competition deployed to 9/11. None of them helped. It wasn't necessarily because they weren't ready, but they weren't. It was that was a very disastrous collapse, and there just weren't a lot of people to save, and there weren't a lot of voids to explore. But it was obvious the robots that were in the competition were not ready for prime time. And then we started getting more serious about the standards development effort. So wheeled robots, legged, tracked, arms, or even people. The test methods started focusing more and more on dividing classes of robots and starting to measure their performance in earnest. And the standards committee gets stood up about a year or two later. And we're agnostic as to the type of robot. Humanoids are welcome to the party when they're ready. I did the DARPA Robotics Challenge around 2015, it ended, and they were, it was a point of measurement, but it wasn't particularly inspiring. If you look now online at what some of these humanoids are doing, it's getting much more inspiring. It's probably due to having another competition to put another mark in the ground. But meanwhile, the ongoing competition that we've done every year since 2000, RoboCup, started with a colleague from Japan, looks just like my building, literally on the south of campus. It's the size of my building. It's all fabricated for 1 week of trials, 700 plus trials in 3 different scales with teams from all over the world, wherever it's hosted, and it moves around the world. So that's a way to both validate the tests and disseminate the tests kind of all at the same time, while instructing the researchers who know nothing about what our firefighter friends do for a living, that if they just focus on doing the tests well, they'll get an audience with those responders. They win this competition, they come to a field exercise. So the competitions are, really popular. Tens of thousands of budding engineers succeeding, failing, but learning the whole way through. Every part of the competition is intense and collegial, and they help each other through because the model has them focused on we, the humans, and our friends, the robots, all working against the disaster that is in front of us. So now we have this new quadruped robot competition. I just want to show you what some of the latest robots, this is literally from last month, what the latest 4-legged robots are doing, if you thought those first videos were impressive. So the competition, the quadruped competition, now they're in all our competitions now, but there was a focused quadruped competition that happens at the major robotics conferences. That's what's new. They start wearing their payloads, they start putting wheels on. So now we're talking about legs, 4 legs with wheels. Wheels that can be braked, wheels that can take you up flat surfaces very quickly with much less energy, although I have yet to measure how much less energy because these are literally so brand new. But that's the idea. So here in the lower left, you see one of my guys in his first 30 seconds operating that robot through the entirety of the terrain that's set up. It's a demonstration. He's eyes on, cheating, but there's no camera on board yet. So this is how we're going to figure out that the mobility is special and the autonomy is special. But doing it as a remote operator is really how you get into the competition and then eventually get deployed. So these robots climbing things above their eye level, it is an advent in technology, an advent in autonomy. And when I first came, this shows up at the competition, and I am amazed. I've seen 2 step functions in improvement in my career, and this is the second one. First one was when the drones started flying and station keeping for themselves. So robot comes up to a loading dock or a wall, pushes up through it like it's a swimmer getting out of a pool. The test method that helps measure that, the only hesitation, the guy on the left is the owner of the company, he's the developer, he knows what he's doing. The one on the right is a complete novice, doesn't know anything about the interface. So the only hesitation is me convincing them while I'm video recording to just push forward. Just push forward. He's like, what? And it just climbs. That's autonomy. So it took me a little while to catch my breath and to focus on what I needed to focus on, which is what the interface looks like. So here you see in the lower left what his thumbs are doing. He's got a thumb for forward and back. He's got another thumb for kind of yaw left or right, rotate. And he's hard over on all those things. He's not massaging this thing at all. He is just putting high-level judgment into that autonomous system and saying, I want to go that way this fast. And it's figuring out all the rest. All the rest as in, when am I braking? When am I leaning? When do I have my arms out here? When do I have my arms in here? So all these test methods are already there waiting for this next advent in technology. They all have settings that go as difficult as possible. It's my job now to make sure that that technology gets measured to its fullest, starting literally this month. Okay, so let me just take you quickly through the aerial drone tests. So drones, you may have noticed, are taking over the world. They are very, very smart beasts. as smart as that guy. We've developed 5 levels of capability to be measured. They break down with open areas. You can think flying around a field. You can think obstructed, which is up close to a building. And then there's confined, which is inside or underneath or inside voids. The idea is that these buckets on the ground give you verge points where you know where you're supposed to be. So the idea is that a test method has to have repeatability. The repeatability is in, are you in the position where you see both buckets at the same time? If you can see the targets at the bottom of the bucket, you're in the right spot. Move on, or work your interface to score the points. Whatever is inside the bucket, and we start with visual acuity and color acuity, those are the basics. You could put objects of interest, you can put anything you want in there, thermal signatures, and we play with all those variables. So here's a video of what one of our validation exercises look like. So this week we're at the Unmanned Tactical Applications Conference, which is hosted at the Guardian Centers in Perry, Georgia. We're here because there's a gathering of 100 or more emergency responders from around the country, internationally too. Military, civilian, public safety, emergency response, a real wide swath of the user community that have been adopting our aerial tests. This week in particular, we validated that the open, obstructed, and new confined lanes work as evaluations of remote pilot proficiency. We use these tests to enable direct measurements of remote pilot proficiency as they credential and license their pilots. The 5 levels are in rough order of difficulty. Level 1 is the basic proficiency or safety check ride. That would be the Part 107 accompaniment, a skills test that goes with the knowledge required by the FAA to fly in the national airspace. Level 2 is more of a maneuvering challenge with 5 different flight paths all in the open test lane. Level 3 is the payload functionality variant of the open test lane. This was always the original intent for open area identification of ground objects. So there's 5 different test methods, 5 different flight paths, all requiring panning, tilting, zooming of their onboard camera, adjusting contrast as necessary because the white and black buckets have different levels of lighting to identify the visual acuity targets that are inside. Level 3 is considered the minimum requirement for emergency response and public safety pilots. Level 4 is the obstructed test lane. That's flying in close proximity to objects of interest. In this case, it can be walls, it can be looking in windows and clearing doorways in structures that are intact, or in collapsed structures or semi-collapsed structures where people ought not be. The obstructed test lane evaluates drones flying within 6 feet or so, 2 meters of the object of interest, and provides 2 buckets verging at a point so they can triangulate their position and know that they're safe, even though they're very close to the object itself. At that point, they have to work their operator interface to, again, pan, tilt, zoom their camera and control exposure to score visual acuity points. Level 5 is our confined test lane. The confined test lane is for indoor, dark, GPS denied situations. It doesn't have to be fully indoors. It can be in confined spaces of semi-collapsed structures. The confined test lanes take place in 8-foot cubic confinements, so there is nowhere to escape. You cannot lose control at any time. You have to stay off all the walls while performing the operationally significant tasks. Very similar or exactly similar to the obstructed test lane, just half scale. The confined test lane is for underbody search of vehicles It is any mission that requires very tight tolerances on station keeping. So I just want to show you what we did last month in Texas, which is the development of the final pieces of that puzzle, which is the confined scenarios that go with those confined tests you just saw. Every test method has an embedded scenario that gets them closer to reality, but not fully immersed in the chaotic reality of their day jobs. So in this case, flying very close in attics, in subterranean voids, where the prop wash is the problem. Your own prop wash cycling through pushes your drone around. It takes a high level of autonomy for it to negotiate these environments, stay off the walls. So levels 1 through 5 are now complete in my mind, and so they'll go to the standards committee and get balloted on. What you see here is what's happening with the licensing of drone pilots. So as I mentioned in there, the FAA makes sure that you have a license, but currently the license is a knowledge exam. This is the practical skills, the driving test, the parallel parking equivalent of drone flight. And it happens to be happening in NFL stadiums that are held all over the place. The scores that come out of those are what you can threshold on and say pass-fail. That's the idea. They're not our pass-fail numbers. They're the credentialing body's pass-fail numbers. And so that is really what people are going to look back on and say, that's what NIST did, was they got, well, first they developed a test method that was quantitative for a newly emerging safety issue, which is drones in the national airspace. And we got it out to our country and really throughout the world as a metric that people can use to coordinate their airspace. 700 is just the Airborne Public Safety Association. There are other credentialing bodies. We're well over thousands. And along the way, we've helped a variety of federal, state, and local responders ramp up their programs, including our Montgomery County Police here and their equivalents in Japan. I just happen to have the Japan slide because my longtime colleague was presenting with me in Texas. Okay, so just one last thing to show you that's really interesting because it was student-led. The students that we have here on campus in the summers, we do high school students, but this was college, undergrad students from last year working on wildfire test methods, incipient wildfire, meaning the first tree where the lightning strike happened, not the front that it becomes, which is hard for a drone to do anything about. This is the idea of this thousands of those lightning strikes, like in Colorado after a thunderstorm. And the state fire folks, they fly behind those storms and they use thermal imagery to make sure, or to map where those locations are so they know when things are getting out of hand. So we devised a test that could help the researchers working in the thermal world and in the autonomous world to put together those systems on a drone that could bring suppressants. Might be water, might be powder, not our decision. So we invented this Spot Fire Omni and the Tree Fire Post. Follows all the same rules you just saw, except it's metal so that we can light some fires inside them when we're ready. First, they start with like a reptile bulb that is as hot as a fire. And you can tell when they're aligned because the temperature says so. And they're doing all their flight paths based on the thermal imagery rather than the visual imagery. And we're using basic, barbecue style burning products. When it's burning, it's confined, it's safe, you can use it outdoors, but the idea is that all the practice should be done with the electric version until you're ready to start spraying water. When you start spraying water, we were interested in whether we could capture the water and measure how much suppressant got on the fire during that trial. And of course, do 10 trials. We'll take your best, we'll take your average, whatever it is. This is just an example of one that did go out. One of 5 in this case went out. The others are still burning. So, controlling how much water, what the directed application of that water is, that's the trick. And that's for the researchers to solve. That's for the competitions to solve. Here you see a basic drone that does crop dusting. Crop dusters exist in nature. We used one because it already has water on board. Not the right tool in the end, in all likelihood. I think they could do better with a directed pointing wand, but we'll see. And again, we're not vested in the outcome, we're vested in the process. The process is to make sure that everyone understands that firefighting drones need to happen. And there is a test method to help corral the research and focus it toward the commercial market. We're here in Reveille Proving Grounds in Burnett, Texas. We're validating standard test methods for underwater vehicles. Reveille Proving Grounds is the only facility in the U.S. using NIST tests for all three phases: aerial drones, ground robots, and underwater ROVs. We're here with a roster of emergency responders from around the country. They help to generally develop the test methods and validate them with their use cases in mind. So you'll see us standing around this frac tank here. Frac tank is the clear water baseline test environment. No excuses. It's clear, it's still to start with, and we can all see the behaviors of the underwater ROV as it's trying to perform the various tasks. And the tasks include non-contact inspection in these omnidimensional C-frames. There's a grasp task. You see where they have to pull the floats to disengage. That's the equivalent of maybe grabbing a backpack off the bottom of the water and bringing it to shore. There's a hook task. Hook task can either involve the grasping device on the ROV, or it might be to hook a secondary pull line. Here on site, we have a deep water quarry, which is relatively clear. And we then transition the test methods to the dock in the quarry, so we start dealing with more operationally significant water. That means they can't see as far. Not being able to see as far means you need to start bringing other sensors into play, sonars, for example, to move around objects, to station keep. So the third body of water here at Reveille Proving Grounds is their pond. We embedded sonar targets in known locations at the bottom of the pond. These are our props. They are not operationally significant. They are just easy to replicate all over the world and easy to implement as a search task. So developing test methods and validating those test methods means you're exercising both the equipment and the test method at the same time. So we put the test methods in front of a wide variety of system capabilities. Those systems sometimes aren't performing particularly well in the test. That doesn't mean it isn't a good test, but the tests have to measure from relatively poor performance all the way through to excellent performance, maybe even beyond the state of the science. So our test methods capture all the performance and put them on the same measuring stick. And that's ultimately how you can compare system to system to system. But what we did here also with some of the responders that came is we used the frac tank and the first two tests, non-contact inspection and the soft grab test, as remote operator training and evaluation process. So we've done this with the drones in the air. It's very popular worldwide. Having 10-minute trials or 5-minute trials in a known environment that is replicated everywhere and can be performed every 6 months or so is a way to ensure the proficiency of the remote operators, which is a very perishable skill, and ultimately to potentially credential those operators as competent. That's happening in the drone space. it's probably going to happen in the underwater space, and having standard test methods as the underlying measurement science is the key to making it all happen. So, that said, I would say I'm open to questions if you guys don't have any place to be. We can stay here. I've got more video. I've got endless video, obviously. I can say that our building is getting expanded. Usually I do this today as a tour, but I guess we got to a lot more of the students this way because the tour is somewhat limited.